In this lesson, we're going to look at a fascinating and exciting technique in organic chemistry called mass spectrometry. Mass spectrometry is a way to weigh individual molecules, and it's really quite an amazing technique. And the reason is that you can imagine how we typically weigh objects. We usually put them on a scale, which is comprised of a spring. The object pushes down on the spring, and based on how much push that object gives, we can figure out how heavy the object is. But that's never going to work for an organic molecule. They're way too small. But with mass spectrometry, we can actually determine how much an individual molecule weighs. Let me show you how it works. It's quite ingenious. So just to kind of tell you what the technique does, weighs molecules. Let me show you how this works. It all starts with something called an electron gun. So the electron gun looks nothing like this, but I'll draw a pistol just to kind of, that was something object that we're familiar with. And this is the electron gun. So it doesn't shoot bullets, but it shoots electrons. So this is an electron gun. This is sometimes also called the source. And what is this electron gun aimed at? Well, it's aimed at your sample, which is an organic molecule. So let's just say our organic molecule is this ketone, for example. When the electrons strike the ketone, they hit it with tremendous force. And they hit this molecule with so much force that they can, with a slight probability, eject a molecule. Eject an electron from the molecule. So it hits it, kaboom, there's a collision. And that's what that green sort of stuff indicates. And then after the molecule is hit with the electron, it loses an electron. One gets knocked out, and so it gains a positive charge. Obviously, if a molecule loses an electron, it's going to become positively charged. And so we indicate that by putting this molecule in brackets, and the plus sign indicates that it has a positive charge, and this little dot shows that it's lost one electron. Okay, that's all great. How is that going to help us weigh the molecule? Well, here's where the clever part comes in. After the sample gets hit by the source of electrons, it enters a sort of gauntlet or a arena. And in this arena, there are two metal plates. And at the end of the arena is a vacuum that sucks everything to a waste container. So you wouldn't want all this stuff to get like crudded up inside of this so-called arena. So there's a vacuum that sucks it all to a waste bottle that you can then pour down the sink. Okay, but the fun part actually happens right in here in this gauntlet. The top plate is positively charged. So it's charged. And the bottom plate is negatively charged. Okay? And so the molecules, they're going to go right through the arena, no problem, right? Not quite. Imagine one of the molecules that enters this arena has a positive charge. Like a lot of them are going to have, right? Because they've been hit by electrons. So they've been ionized and now they have a positive charge. They're not going to go straight through this arena anymore. They're going to be deflected because they're going to be attracted towards the negative side. So any positively charged molecules will be deflected and collide with the plate at the bottom. Now, where it hits on the plate is a function of that molecule's mass. Because if the molecule is really heavy, it's going to have a lot of inertia. So it's going to be very, very difficult to distort it from its original path. But if the molecule weighs basically nothing, it's going to be as light as a feather, it's going to be very strongly attracted to the negative plate. It's not going to have much inertia to keep it moving in a straight direction, so it hits the plate early. So what that means is that heavy compounds hit the plate towards the end of the arena, and light molecules hit the plate almost immediately. Now, the reality is most of the stuff goes straight through to the waste because this electron collision only happens a very rare percentage of the time. So that's actually a good thing, because you wouldn't want these plates to get filled up with tons of crud. Another nice thing is this method works with very, very, very small amounts of material. So you only need a very tiny amount of the sample, and you'd only want a tiny amount of the sample, because over time you have to clean this crap out, and it gets very messy, and it's a very hard job, and it's not a fun job, and I've had to do it before, and it's nasty. Okay, because you can imagine if you've got 32 students all running samples on the mass spectrometer, things are going to get pretty dirty pretty quickly. Okay, so that is the principle of how this device works. And so there's a detector on this plate that detects when and where something hits it. And it counts how many collisions occur at that certain position. And what you end up creating is a plot that looks like this. Beautiful plot. Wow, what does it represent? Well, along the x-axis you have the mass, and the mass is in AMU, so atomic mass units. These are the same masses that you find on the periodic table, so like the atomic mass of a compound, it's the same units down here at the bottom. And you'll see that M over Z. The Z has to do with the charge, M is mass, don't worry about the Z part, just assume for the purposes of this class, it's measuring mass. And so, that's interesting. It seems that there are multiple peaks in our mass spectrum of this compound. Why are there multiple peaks? You might think, oh, maybe there are impurities in our compound, and that's what each peak is referring to, an impurity, but you would be incorrect. Let's take a close look at what this graph represents. So the most important thing you want to look for is the highest peak. And in this case, the highest peak is labeled with an 86. This peak is called the M plus peak. M plus because M stands for the molecule with a plus charge. So this is called the M plus peak. And then if you look right next to the M plus peak, can you see there's a little something there? Let me zoom right in here. So not quite the heaviest peak. The heaviest major peak is the M plus peak, but there's this little tiny something, looks like a hair, down there next to it at 87. That is the M plus 1 peak. And that's a very important peak. We'll talk about the M plus 1 peak a little bit and what that tells us. Okay, and there's one other peak I want to mention here, and that is going to be 43. Notice this huge tall peak. Sometimes it'll be in the middle, sometimes it'll be at the top. You never quite know where this tallest peak is going to be, but this one is called the base peak. Wherever the tallest peak is, that one is called the base peak. Okay, so let me just sort of define these terms over here. So tallest equals base peak. Heavy peak, that is the peak way to the right, is called the M plus peak. And heavy plus 1 is the M plus 1 peak. And these things all tell us a slightly different story. The heavy peak, the M plus peak, is sometimes called the parent ion, and that tells you the molecular weight. So in many respects, this is the most important peak, the M plus peak, because it tells you how much the molecule weighs. If the M plus peak is at 86, that tells me that this molecule 2-pentanone weighs 86 AMU. That's super useful information. Okay. The heavy plus 1 peak, the M plus 1 peak, that is due to the presence of carbon-13. Since we are weighing organic molecules, we have to remember that there's an isotope of carbon that exists with pretty high abundance, 1.1%. abundance. So because there's always that 1% chance that a molecule is going to have a C13 in it, there's always this tiny little peak down here that's corresponding to the molecule with one C13 inside of it. Sorry, got my headphones. Those over there. Okay. Now, I never mentioned about this base peak. What's going on? Well, it turns out that when you shoot a molecule with electrons, yeah, sometimes you knock off an electron, give it a positive charge, but sometimes you also cause the molecule to break into pieces. And so these little peaks down here are pieces of the molecule called fragments. So all these things here, boom, 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 these are fragments, including the base peak. In this situation, the base peak happens to be coming from a fragment. So whatever that means, whatever that fragment is that weighs 43, that's a very, very abundant fragment. That means for whatever reason, when this molecule gets hit with electrons, it breaks apart into a piece that weighs 43 quite often. Now, we could go into a deep analysis and try and figure out what that piece is that broke off that weighs 43, but we're not going to worry about that in this class. We just don't have enough time. But it's pretty fun. So if that interests you, I'd be happy to talk with you more about how to figure out what all the different fragments are, but really we don't care about any of that. All we care about is, can we label a mass spectrum like this? Can we find the M plus peak? Can we find the M plus 1 peak? And can we find the base peak? And then can we look at the M plus peak and figure out the molecular weight of the compound? By the way, the fragments are sometimes called the daughter ions. So just look for that term if you see that anywhere. So let's take a look at an example and label the peaks. Okay, here is a mass spectrum of benzene, one of our favorite compounds. And can you find for me the base peak? That's right, the base peak is the tallest peak. So that's going to be right here at 78. Can you find the M plus peak? That is the heaviest peak. The heaviest major peak, I should say. No, it turns out in this case, the base peak is also the M plus peak, which is also called the parent ion. Okay, can you find the M plus 1 peak? Yep, it's right down here. All right. Who are my daughter ions? My daughter ions are all of these guys down here. All of these are my daughter ions. We don't know exactly what they are, but they are fragments of the benzene. And this is kind of interesting, and this is kind of what we would expect. Notice that in this case, the base peak and the parent ion are the same. What that means is that this molecule doesn't like to fragment very much. It means that most of the time, when this gets hit with an electron, it just loses an electron and none of the bonds break. And that kind of makes sense for benzene, doesn't it? Because it's an aromatic molecule, it's very stable, so it's very hard to break it up into pieces. Versus the previous molecule, the base peak was way down here at 43, which meant it was coming from a fragment. Maybe that makes more sense. This molecule isn't as stable as benzene. It's more prone to breaking into pieces. So all of this, hopefully it makes sense. It's pretty cool, actually, to see this. All right. Let's see what's next here. What can you tell from mass spectrometry? That's what we want to talk about now. What can we tell? Number one, we can tell the molecular weight. How will we tell the molecular weight? Molecular weight, which I sometimes abbreviate MW, we can look at a mass spectrum and determine that by looking at the parent ion. So parent ion mass is going to be equal to the molecular weight. So just keep that in mind. When we look at a mass spectrum, we can figure out the molecular weight of that compound pretty easily. Number two, we can figure out the nitrogen content from mass spec. Really, we can find out how many nitrogens are in a molecule just by looking at the mass spec? Yes and no. We can determine if there's an even or odd number of nitrogens. It's something called the nitrogen rule. The nitrogen rule says that if you have an odd molecular weight, that you have an odd number of nitrogens. For example, you might have 1 nitrogen, but you might also have 3, 5, 7, etc., etc., etc. Now, usually you don't have a molecule with 7 nitrogens, but if you have an odd molecular weight, that might mean you have a nitrogen in your molecule. On the other hand, if you have an even molecular weight, the nitrogen rule says that you will have an even number of nitrogens or no nitrogens at all. So you may have 0, 2, 4, etc., etc. You can find that from the molecular weight. And because you can find the molecular weight from the mass spec, you can also use the nitrogen rule. Number 3. Halogen content. Yes, that's right. You can use mass spectrometry to figure out if your compound contains chlorine or bromine pretty easily. So let me show you what that looks like. It turns out that bromine and chlorine in particular, which are very common in organic molecules, have isotopes that are very, very abundant. So bromine is most obvious. For bromine, you're going to find there's 2 isotopes, bromine 79 and bromine 81. And these isotopes are in a 51 to 49% ratio. What this means is on a mass spec of, and that's mass spec is a short word for a mass spectrum, and one of those spectrums that we looked at on the previous page, if you see doubling of the peaks, they look like 2 lines, like almost like you have double vision. That tells you you have a bromine because of this 1-to-1 ratio of these 2 isotopes that are 2 apart. One weighs 79 and one weighs 81, so you see this doubling of lines, and we'll see an example of that. Chlorine is a little bit more subtle, but also discernible. Chlorine also has 2 relatively abundant isotopes, also 2 apart. There's chlorine 35 and there's chlorine 37. And these have a ratio of 76 to 24. So with chlorine, you'll see like a big peak and then a peak the third of the size next to it by 2. So you see kind of these like slanted doubling of lines. And we'll look at some examples of that. Okay, so then there's also the ability to find detailed structural information about a compound. Some people devote their entire lives just interpreting mass spec information. You can actually find a lot more than just nitrogens and halogens. You can figure out the actual molecular structure, and not just of organic molecules, but of complex molecules like proteins, which are, have atomic masses or molecular weights well into the tens of thousands. So we're not going to do that in this class. We're just going to do the first 3 relatively simple things, so this isn't too bad. Let's take a look at some examples. All right, example number 1. And by the way, I'll upload this worksheet so that you can look at these examples. Which of the following mass spectra correlates to pyridine? So one thing you can notice about this compound right away is that it's got who? It's got what? It's got nitrogen. And you know that if a molecule has an odd number of nitrogens, it's going to have an odd molecular weight. So one of the fastest things we can do is look for the parent ion and figure out if it's an odd or even number. So let's take a look at the first spectrum. Where's our parent ion? You're looking for the heaviest, kind of most abundant ion. And so that's going to be this huge line right here. This is going to be our parent. And now we just need to zoom in really close and figure out what is that at. So our parent is right here. And this is 80, 81, 82. So our parent ion is at 82. And the units are m/z, or 82 AMU. Now 82 is an even number, so that can't be pyridine. So already I know this has to be not pyridine. Let's take a look at the next spectrum. Okay, well this is looking good. Our parent ion's right here. And I can see that it's at 79. Now that's an odd number, and our compound is looking to have 1 nitrogen, which means it needs to have an odd molecular weight, and only the second spectrum has an odd molecular weight. So I don't even need to do any more checking. I know that my answer is number 2, just using the nitrogen rule. Okay, that was pretty easy, right? See, isn't this class easy? Let's go to the next one here. Okay, now let's try and find out which one has halogens in it. So one of these is bromobenzene and the other is chlorobenzene. Just by looking at the patterns, can you figure out which one is which? Remember what I told you about bromine? It has isotopes with a 1-to-1 ratio, so look for the doubling of peaks. So which one of these spectrums seems to have more of a double peak going on? That's right, the first one. You can see this doubling going on right here. So this is going to be evidence of the bromine ion, the bromine being present. And then now let's take a look at the second mass spectrum. Well, we already figured out the first one's the bromine, but can we see convincing evidence that the second one is chlorine? Absolutely. Notice now we have this 3-to-1 ratio that's 2 apart also. So take a look at that. Can you see that there's that 3-to-1 ratio here? That's evidence of chlorine. So the second compound is going to be our chlorobenzene. Okay. Easy. So easy. You can tell about nitrogen just looking at whether your parent ion is even or odd. And you can tell bromine and chlorine just for looking for either the doubling pattern, a 1-to-1 ratio, or the doubling pattern with a 3-to-1 ratio. Okay, now that's all well and easy. And you'll have some practice to do with these on your little worksheet that's due for points. Let's do a little bit of math. Let me show you now how to solve a molecular formula using a mass spectrum. This is the real meat and potatoes here. So solving a molecular formula from mass spectrum. All right, let's say I gave you the following information. And it's usually presented like this: M over Z equals, and then they start listing the peaks. So if they're not going to give you the picture, they can just list the relevant values for you. All right, let's say the M over Z values are 143. And then in parentheses, they're going to specify that this is the parent ion by writing M. Sometimes they write M plus, but usually just write M to show that it's the parent ion. And then comma, the percent abundance. So in this example, the percent abundance of our parent ion is 100%. So what does that tell you about the parent ion? So the M tells you it's a parent ion and the abundance is 100%. That tells you that it happens to be in this example that the parent ion and the base peak are the same thing, because whatever is 100% abundant is the base peak. Okay, the next peak is 144. Now, that must be the M plus 1 peak, and so you'll oftentimes see that written, even though it's pretty obvious that if 143 is the M, and then 144 is the M plus 1, and the abundance is 9.71%. And then 145, M plus 2. Now, M plus 2 is usually only relevant if there's a halogen, like chlorine or bromine. As we saw in the previous pages, there can be an M plus 2 peak. But in this example, the data shows that it's less than 1% abundance for the M plus 2 peak. So what can we immediately tell about this molecule structure just by getting these data points? So immediately we know, number one, the molecular weight is equal to 143. We know that the molecular weight is 143 because the parent ion weighs 143. Number two, nitrogen content. Nitrogens. Well, we know we need to have an odd number of nitrogens because our molecular weight is odd. 143 is an odd number, so the nitrogen rule says we must have 1, 3, 5 nitrogens. Probably not going to have more than 3 in this class, but maybe there's 5. We have to keep that probability open, and that is because the mass is odd. I love that we were able to find so much information with doing so little work. And then number 3 thing that we can find out, halogens. Do we have any halogens? No bromine or chlorine, at least, because the M+2 peak is so small. If there were bromine and chlorine, we would see a very strong M+2 peak, either of 100% or 30% based on our parent ion. So no Br or Cl because no M+2 peak. Okay, but can we find the molecular formula? So we know that the molecular weight is equal to 143. Can we find something that looks like this? CX, HY, OZ, NW, etc., etc., etc. Can we figure out what all those variables are and figure out, is this a C12, H18, O2N? Like, what's the formula for this? So here's a trick. First order of business is to try and find the number of carbons. And we can use the ratio from M and M+1 to find that. So here's the trick. Use the fact that M+1 is due to C13, carbon 13, that has 1.1% abundance. So we can find the M+1 to M ratio. And this will help us figure out how many carbons there are. So what is our M+1 abundance? It's 9.71%. And what is our M abundance? It's 100%. So if we do that division, multiply by 100%, we get 9.71%. It's kind of dumb math, but you'll see how this is going to help us. So then use the following formula. M+1 ratio divided by 1.1%. That is going to tell you approximately how many carbons are in your molecule. So if we do this division, we'll get 9.71% divided by 1.1%. And this is, of course, just approximate. It equals 8.82. So what that tells you is that you have either 8 or 9 carbons. It's close to 9, but you can only really say 8 or 9 carbons. So this helps you to figure out how many carbons there are. And again, let me just show you what we did. We took this number here, divided it by this number, and we got the ratio of M+1 to M. Then we took that number and divided it by the abundance of carbon 13, and we got about 8.8. So that told us that we have 8 or 9 carbons, because 8.8 is somewhere between 8 and 9. All right, so now we just need to try some possibilities and figure out what the molecular formula of this compound could be. Let me get a new piece of paper and we'll try that. Okay, let's just assume for a second 8 carbons. Okay, if there are 8 carbons, then our starting mass was 143, and we're going to subtract from that 96. Why 96? 96 is 12 times 8. 12 is the mass of carbon, and there's 8 of them. So we do 143 minus 96, and that is going to give us 47 AMU. And that 47 AMU means that is the mass that's left over for hydrogen, nitrogen, and oxygen, which are the elements that are likely to be present inside of an organic molecule. Okay, there's not likely to be boron inside of our molecule. The only elements you would ever assume are inside of an organic molecule are carbon, hydrogen, nitrogen, oxygen, and possibly bromine and chlorine if the data suggested that, but the data did not suggest bromine or chlorine was present. Now we can make a table and try and figure out some reasonable molecular formulas. So let's make a table. Column 1 will be oxygens. Column 2 will be nitrogens. And column 3 will be 47 minus the mass of the oxygens minus the mass of the nitrogens. That is going to equal the number of hydrogens, since hydrogens just weigh 1. And then we can figure out the formula. Okay, so let's pretend we have 0 oxygens. We know we need to have an odd number of nitrogens, so let's pretend we have 1 nitrogen. What is that number of hydrogens going to be? Well, we'd have 47 minus 0, because we have no oxygens, minus 14 for 1 nitrogen, and that's going to equal the number of hydrogens as 33. If we do that math. So the formula for this possibility is going to be C8H33N. Okay, that's one possibility. Let's keep going. Now let's pretend we have 1 oxygen and 1 nitrogen. So then our number of hydrogens will be 47 minus 16, that's the mass of oxygen, minus 14, that's the mass of nitrogen, and that's going to give us 17 hydrogens. So our formula would be C8H17NO. Let's try another possibility. Let's say we had 2 oxygens and 1 nitrogen. Then that might be 47 minus 32 for 2 oxygens minus 14 is going to equal 1. So that's going to give us a formula of C8HNO2. And how about, here's a wild possibility. Let's say we had 0 oxygens and 3 nitrogens, because remember, we're allowed to have an odd number of nitrogens, so this is also a possibility. This would be 47 minus 0, because we don't have any oxygens, minus 42, which is 14 times 3. That's going to equal 5. And so then that would be C8H5N3. So we just came up with 4 possible formulas using the mass spec data. All of these formulas add up to 143. You can add up the masses. You do 12 times the number of carbons plus 1 times the number of hydrogens plus 14 times the number of nitrogens, and so on and so forth. All of these will add up to 143. So we know that whatever this mystery structure was, it had one of these formulas. Now, of course, we'd also have to repeat this for the possibility that there were 9 carbons, but for the purposes of time, we won't do that. And so the last thing I want to mention is, are all of these formulas reasonable? There is a maximum hydrogen formula you want to check out. So max hydrogens, because there's a limit to how many hydrogens you can have in a molecule, and that is equal to 2 times the number of carbons plus the number of nitrogens plus 2. That is the maximum hydrogen formula. So I'm looking at the first formula here, and it seems like there's quite a lot of hydrogens in there, 33. So I want to make sure this isn't violating the max H rule. So let's figure out how many hydrogens would be allowed with that formula. So we know that there's 2 times 8 carbons plus 1 nitrogen plus 2. So that's going to be equal to 16 plus 1 plus 2, which is 19. So the maximum number of hydrogens for 8 carbons and 1 nitrogen would be 19 hydrogens, but this formula has 33. So I'm going to put an X by it and say not reasonable. And that's because there's too many hydrogens. If there were 19 or less, then I would say it's reasonable. All the others, though, are reasonable. And so this might be an example problem, and you'll see that this is a problem on your little handout to do, is just to provide some reasonable molecular formulas for a given mass spec data. All right, should we do one more just for practice? Let's do one more just for practice. Okay, I've provided some M over Z data for you. I see that the M over Z ratio is 136 for our parent ion with an abundance of 0.05. Our M plus 1 is 137, and it has a percent abundance of 0.0024. And our M plus 2 is 138 with 0.049. So one thing I'm seeing right off the bat is, number one, my molecular weight is equal to my parent ion, which is 136. Number two, no nitrogens or odd number of nitrogens. I'm sorry, no nitrogens or even number, since the nitrogen rule says that if we have an even molecular weight, there's either no nitrogens or an even number of them. And then number three, what about halogens? Well, I'm looking at the M plus 2 peak and I see that, oh, well, this is 0.05 and this is 0.049. Those are basically the same. Which ion has the 1-to-1 ratio? Which halogen has a 1-to-1 ratio? Bromine. So we probably have one bromine in our molecule. Okay, so let's try and figure out what is our carbon count. So for that, we'll do our M plus 1 divided by M ratio. And if we do that, we get 0.0024 divided by 0.05% times 100%. And that gives us 4.8. All right, and then we take our 4.8 and divide it by 1.1. Don't forget to divide by 1.1, and if you do that, you get 4.36%. And, well, the percents cancel. So you get 4.36, which equals probably 4 carbons. So that's a good estimate as to how many carbons this molecule has. It's probably about 4. Could be 5, but probably 4. So let's assume C4 and see if we can figure out the molecular formula. So if we have C4, that would be 136 minus 4 times 12, which is 48. So this is 4 times 12, which is the mass of carbon. And we also think there's a bromine, so minus 79 for the bromine. That's only going to leave us 9. 9 left for hydrogen, oxygen, nitrogen. Well, one nitrogen weighs 14 and an oxygen weighs 16, but we only have 9 mass units left. So all of those 9 must be due to hydrogen. So we pretty much figured out the formula. There's only one possibility. The 79 is for 1Br. So pretty much our only possibility is C4, H9, Br. So it's kind of a trial and error process, but there's some tricks to it. The big trick is, of course, using the M plus 1 to M ratio, dividing that by 1.1 to figure out the number of carbons. Then subtracting the mass of carbon from the molecular weight and subtracting any halogens that may be present to figure out how much mass is left for other elements like hydrogen, oxygen, and nitrogen. And then trying all the different possibilities and seeing if they're all reasonable. Okay, so that's pretty much all you need to know about mass spec. So now that you've watched this video, why don't you try the guided worksheet and see if you can solve the problems that I provided to you. Okay, bye for now.